Hello, everyone. Hi, Professor Vishwanath. Good to see you.
Good to see you too. Good afternoon.
Yeah, good afternoon. Hi, everyone who else is joining from everywhere in the world. Welcome to the Binance Academy live webinar. I'm Nina Xiang, part of the Binance Academy team. Binance Academy's mission is to teach everyone about blockchain technology, and we're one of the largest learning hubs in the industry. So please follow us on YouTube, Twitter, and other social media channels to stay tuned with upcoming webinars and other great educational content from us. So today we're very happy to have Dr. Sriram
Got it?
Vishwanath, a professor at the University of Texas, joining us for a discussion on the topic of blockchain scaling solutions. So a very timely topic to talk about today. And Sriram, I'll just call you by your first name. And good to see you. And thank you so much for joining us today.
Nina, thank you very much for having me. It's a pleasure being here. I'm looking forward to sharing more about scalability. I understand this will be an interactive session, so please fire away with questions. I'm looking forward to discussing how scalability is not just impactful for blockchains, but ultimately will determine the fate of the whole industry. So I think
Yeah.
it's one of the most fundamental things for research to impact both the near term and long term of blockchains.
Yeah, and exactly. You have done a lot of research on blockchain scaling solutions. And, it's very timely because considering what's going to happen with the Ethereum merge, which is also quite relevant to scaling one of the largest blockchain networks currently we have in the world. So we're going to probably, let's see if we can have time to touch a little bit on that. But really,
Yep.
today's session is to give everybody a foundation understanding of what is scaling solutions, why do we need them, what kind of solutions are there already, and what are we exploring right now and for the future. So to cover all that, we're going to go into a presentation that Professor has very generously put together. So we'll put that up for now. Um, so maybe first question, let's talk about, why do we need blockchain scaling solutions?
Sure thing. So, Nina
Or
and
maybe a self introduction
I,
first.
yeah,
Sorry.
let me introduce myself, and then I'll talk a little bit about blockchains and scalability and why it's been a challenge. Why scalability has always been an issue in and continues to be an issue in blockchains and Web3, and why scalability was an issue in Web2 but was easily done. Web2 had an easier time, while Web3 is having a tougher time, and we'll go into that in more detail. So, again, my name is Sriram Vishwanath. I'm a professor at the University of Texas. That's me maybe 5 years ago with a lot more hair. I've lost hair since then, but I'm I'm in the Cochrane School of Engineering. So I'm an engineer by training. I switched to teaching and running, blockchain classes about 4-ish years ago. Um, and then I also incubate blockchain ideas. So if you have any ideas that you want to share with me, please do, because I enjoy learning and coming up with new ideas in the space, and scalability is one of them. Moving on to the next slide. So, and one thing I want to preface is my slides are fairly technical. Uh, the discussion doesn't have to be technical. I'm happy to talk much more about the general concepts of blockchains and what makes scalability so difficult. But as I go along, the slide deck will have a lot more technical depth as to how blockchains work and what makes them tick, and then what makes scalability such a challenge. So, as you know, blockchains are a chain of blocks. Here is an example of, I think, 3 blocks from an existing chain. This might be Bitcoin as an example. I often use Bitcoin as an example because it's a classical example. Blockchain doesn't matter if it's Bitcoin, Ethereum, any other chain. Typically, what you have is a set of what are called blocks, and the set of blocks are arranged in some format, in this case, a chain. It's also called a hash linked list. If you hear the term hash linked list, very often blockchains can be called hash linked list. It is not really a technical term, so you can think of this very much in English. There's a set of hashes. These hashes link with one another in a backwards manner. So, for example, this block 52 is linked backwards with this block 51 through what's called a hash. And it's a list. So it is many different blocks in a list format connected through hashes. Okay, now there's a monetary cost to connecting these. There's often something called fees or associated block reward. And so, together with a proof of X, proof of work as an example in Bitcoin, proof of stake, proof of various different proofs you can have. Proof of X is what I'll call it, which ultimately provides a measure of security. You have what's called a blockchain. So a hash linked list with a proof mechanism with a certain cost associated with writing a block. Okay, so that's a basic blockchain. So moving on from that, next slide. And folks, I'm initially just talking about basics to explain why scalability is so hard, and then we'll go into scalability and solutions themselves. A proof of work is an example proving mechanism. There's many others that we do today, although proof of work remains something that we've been doing for quite a long time. So from the very beginning, proof of work, by beginning I mean January 3rd, 2009, when Bitcoin was launched, we've been doing proof of work as one of the security mechanisms. And the way it simply works is there is a mechanism of proving that proof of work is a mechanism of proving that a particular block has sufficient work in it, has sufficient compute in it, has sufficient resources dedicated to it. And once that is done, you're able to define a particular block as the canonical block, as the main block, using which you're able to build a chain. So many people produce blocks. The block with the right amount of work or the right amount of resources, the right amount of, in this case, hashing that has been done is the canonical next block, right? Now, there is something called longest chain rule, which is the next slide. If you move on, Nina.
It's actually very interesting, this slide. We can see the basic proof of work algorithm,
Yes.
this whole process. So, for a lot of people, we might have a very basic understanding of proof of work, but it's actually a lot of all this, programming algorithm
It
in
is.
the back end.
It is. So it is a proof of work, again, and the main reason I'm using proof of work as a canonical example here is that it is the oldest. This is where it all started, right? We did a basic proof of work algorithm now more than 13 years ago. In fact, it predates that. We've been doing proof of work like things even prior to that. So it's a classical example of how you secure a chain. And why securing a chain is important is that if you did not have a security mechanism like proof of X, in particular case proof of work, you would not have much of the decentralized behavior we want from a chain. And if you don't have the decentralized behavior, we don't have much of the security that is needed to do transactions. So all of this ties into what makes blockchain unique. We have a
And also makes the scaling
also makes
difficult.
scaling difficult. Exactly,
Right.
100%, Nina. So whether it be different proof of X mechanisms have challenges when it comes to scalability, primarily because you have to deliver this proof, and this proof has to be done in a decentralized way. And when you make all those constraints, you have to deliver this proof, it has to be done, this consensus has to be a decentralized way is what makes scaling so hard. So moving on. Next slide.
Right. Yeah.
So,
So the longest chain rule.
so the longest chain rule, and again, you might have heard of this. If you've never heard of it, I'm happy to explain it to you here. So the longest chain rule is or heaviest chain rule, or weighted longest chain rule, are the various rules. Uh, Again, this is a very classical rule. There's various versions of this rule since its inception, but it's essentially to achieve consensus. So every node has to agree on what the canonical chain is. Canonical means the chain that everybody agrees on, right? Now, this is a big problem in blockchains. And there's a big problem in blockchains because people all over the world, or all over a distributed system, in this particular case, decentralized system, nodes everywhere, that's what it means, have to agree. And so this agreement process uses something called longest chain rule, where different players, they're called miners in the Bitcoin world or the classical Ethereum world, they could be called stakers, they could be called, let's just call them players, okay? Have to agree on a particular chain being the longest chain. And when they agree on that, they decide which block makes it into the chain and which blocks are left out. The blocks that are left out could be called uncles, could be called selfish mining blocks, could be different types of other blocks that are not in the chain. This process enables you to hit what's called consensus so long as the adversary does not control the network. By control the network means has more than 51% of power on the network. This power could be hashing power in the case of proof of work, could be staking power in the case of proof of stake, and so on. So as long as the adversary doesn't control the network, you need to be able to come up with a mechanism where honest people can agree and therefore achieve this thing called consensus. Now, this is the classical problem. This is what makes scaling so hard. So again, we had this thing called hash linked lists. This hash linked list was given to multiple people across the world. They had a proof mechanism, and then they all had to agree on what the chain canonically is, or was. And this is the basics of a blockchain. All of this coming together causes a lot of issues. So let me now list what are the issues that cause a blockchain not to scale very well. One of the, and there's many issues. Anybody who tells you there's only one or two issues is looking at one limited perspective of it. There's about 8 or 9. Actually, I made a list of them. There's about 9 issues. So each one of which limits scalability. Let me give you some of the more classical ones, and then we'll go into the less classical ones. So one of the most classical issues is called network latency. So what's network latency? Network latency is where information from one part of the network takes a certain amount of time to get to another part of the network. And that latency, often called round trip time, limits to what extent nodes can work together. In fact, if the latency is very high, consensus time will be very slow. Okay, there's a further factor, and I don't have a slide on it, so I'm just going to talk about it. In databases, there's a famous theorem called the CAP theorem. And if you haven't heard that theorem, it's actually a very old, many decade-old theorem that says that in no database can you achieve. And remember, blockchain is a decentralized database. It has transactions that go into the block that everybody has. And so in many ways, whatever doesn't work for databases also does not work for blockchains, meaning if databases cannot do it, then blockchains also cannot do it. So what is the CAP theorem? It stands for CAP theorem. Please search it. You can, if you search for CAP theorem, it'll show up in whatever search engine you use. But CAP stands for consistency, availability, and partition tolerance. So the theorem states this: at no time can you have all three. You cannot have consistency, availability, and partition tolerance. If your database is consistent and available, it will not be partition tolerant. If it is available,
is that also a trilemma? Because we know that in the blockchain space, there are so many trilemmas.
Yeah. So the CAP theorem is the classical trilemma, which is in the blockchain space, we've been coming up with trilemmas that are effectively the CAP trilemma. Okay, so what that means is the CAP theorem is so old. It belongs to databases from the, I don't know when it was first stated, maybe 80s, right? Maybe 70s. I don't know how old it is. So it's anywhere, it's about 40 plus years old. So what it says, it's the first trilemma. Okay, the trilemma says that you cannot have, if you have consistency, you won't have, and availability, you will not have partition tolerance. If you have any two, you will not have the third, right? If you have availability and partition tolerance, you will not have consistency, etc. Now, this is a theorem. That means people can tell you, no, I managed to get all three, and they're lying to you effectively. You cannot have all three. That's the problem. So because we cannot have all three, blockchains suffer from scalability issues. So let me explain what I mean. What is consistency? Consistency is everybody agrees on the information. Okay, that means that if you have n distributed nodes, they all agree on what that shared information is, the same database value. Availability. Availability means if I request data, I get the data. That's availability. I go to a node and say, show me the data. And if you all have the same data that's available, or the data is available for you to read and write to, that is availability. Partition tolerance is to what extent can I break the network up? So let's say the network has 1,000 people. If I can partition network, I can say, okay, you go on one side, you go on the other side, don't talk to each other. That is called partition tolerance. That means the more I can partition network, the more I can break it up, the more tolerant it is to partition. Does it make sense? So it's as in English. Partition tolerance means break it up. How much
It's
break it up?
right. It's quite it's very very technical. I think we get the idea of
Okay.
this trilemma, this trade-off, that for scalability we also have the scalability trilemma,
Yes.
which is very much very much corresponds to what you just said.
Yes.
But yeah, maybe we can
Let me
just come
let me
back
move
to
on.
the
Yeah.
right. Okay.
Yeah. Let me come back to it. So CAP theorem is one of the classical reasons why scalability is so hard, which is if you have any of these factors, for you to scale a lot of transactions is very hard, because if you try to scale more transactions, you have to have a network that is consistent and available, right? So for various, all of the CAP theorem is a fundamental bottleneck. Okay, there's a third or fourth bottleneck I'll list, and then we'll go into what solutions exist. Third bottleneck is very much IO, input output. So there is a latency, there's a delay in how fast you can read and write stuff. Fourth factor is called load balancing, which is as you have information coming in, you need to load balance it effectively across the network. And then these are just four factors. There's about five others, as I mentioned. The 9 factors that I listed, at minimum, they may be even more to enable.
I think we get the idea now why scalability has been so challenging.
Yeah.
So can we go to maybe
Yeah. Let's,
the slides where you're going to explain about
sure.
double spend attack and how
Yes.
that makes scalability difficult too.
Yes. So let me speak to double spend attack, and this also makes scalability challenging. Thank you, Nina. So a double spend attack is a attack where somebody tries to buy a item and then secretly constructs a fake blockchain saying that they did not spend anything. And I'm giving BTC as the example. Same thing applies to ETH. Same thing applies to BNB. Same thing applies to others as well. So they do what is this is called a selfish mining type attack, but you can do different types of attacks of this nature, where you secretly contest a blockchain and then you hide this blockchain from the main chain, and then you release it and try to keep both the yacht and the BTC. Now, this is a major problem because it leads to side chains being created, and the side chain causes further scalability issues. So it causes what I call soft forks. It produces all of these additional chains on the side through adversarial attacks. Okay, so overall scalability challenge is blockchain that's distributed. It can be attacked like this. and it can lead to something called uncling. It can lead to many types of sidechains. So as you know, and this is very well known, classically, Bitcoin, Ethereum, many others are scaling limited. We're looking at 10 or 15 TPS. Now, I want to explain to you why scalability is so important. I don't have a slide on that, so I'll speak to it. Scalability is so important because you need to be able to do thousands of TPS to be able to build a sustainable blockchain ecosystem. Why do you need that? Why can't 10, 15 TPS be enough? The reason is that the fees can climb up substantially when the TPS is low. And the more the fees climb up, the harder it is to secure the network, the more expensive it is to use the network. So if you want a low fee, ideally, a few cents, even lower than that, network, you need to be able to scale the network to thousands of transactions. So across all the transactions, you have sufficient fees to secure the network. Hopefully that made sense. Right, Nina?
Yeah. Yes.
Okay.
And also, I think like aside from transactions per second, there is also this need for, when you think about Web3, when we think about we want to build an alternative social media platform, for example, then we're looking at processing data on the blockchain on the scale, much, much higher than what, credit card companies can do nowadays. So in order to achieve that goal, that means we have so much more we need to do on the scalability front. So
Yes, absolutely. Absolutely.
yeah,
So to emphasize what Nina just said, it's not just beyond credit card companies today are able to do 7,000 plus TPS, let's say 10,000 TPS. But that isn't our limit. We want to go even higher than that. And the reason is we want to enable a whole host of new applications. We want to enable a whole generation of new AR, VR, gaming, new dApps that never existed before. And so we would like tens to hundreds of thousands of TPS to support those applications. All right.
exactly.
So let's get into different scaling principles. And again, I'll speak about this more than the slide deck. So one approach is to build scalable layer one, and it's very doable. We just have to. It's a lot of hard work, but it's very doable. So let's speak to scalable layer one, and then we'll speak to if you don't have the scalable layer one, then scale through layer two, right? And how you do go about that. So there's many approaches to this. As you know, we just talked about the merge, moving off of proof of work so as to secure it through other principles beyond proof of work. And there is staking is perhaps the most popular approach in that respect, but there's other approaches too. People have talked about various different principles by which security guarantees can be provided while improving scalability all at the same time. So that's one approach. The other approach is to really think through how you'd re-architect these networks. And I'll talk a little bit about that in my research, where you introduce new mechanisms of load balancing, new mechanisms of constructing databases, etc.
Um,
So,
can I ask a question in terms of changing the proof of work to proof of stake? Is that for scaling purposes, or is that for more for energy environmental footprint purposes? Because I thought a primary reason for Ethereum changing to proof of work or proof of stake is for energy consumption.
so you're absolutely right there. So the changing the proof of X basis to make it scale better is not often the okay. So answering the other way, you're right that the Ethereum merge will have an impact on energy consumption and less of an impact on scalability. That's absolutely correct. In fact, in many cases, changing the proof doesn't do anything to scalability. I've listed it here primarily because there are people and there are mechanisms that have claimed better scalability by changing the proof. But in general, by changing the proof, it doesn't have a significant impact on scalability it has a significant impact on energy consumption. So, to your point, changing the proof of X is much more an energy per bit calculation or energy per hash calculation than it is a scalability calculation. So correct.
But if you do change to proof of stake, then you actually set up a foundation for easier scalability solutions in the future, like sharding. So what Ethereum is planning to do after the merge is that they will do sharding next.
Yes, and there are sharding mechanisms that could be beneficial from a scalability perspective, but again, the proof mechanism and scalability have a vague relationship. What that means is that the proof mechanism isn't directly connected with scalability.
Got it.
Sharding and other principles can work with multiple proof mechanisms. They're not dependent on proof of stake. So the summary of it is, you're absolutely right in that there is tangential benefits that come out of changing with the merge, but the proof mechanism itself does not directly influence scalability. That's correct. Okay. Now, coming back. Yes, so you can come up with new architectures to enable scalability. Ethereum has come up with a classical architecture for that. Polkadot has come up with an architecture for that. And there's other architectures that have been developed across the community. I'm just giving examples. I'll talk about one architecture that my research led up to in future slides. But that's just layer one, right? Now, you can also do scalability in layer two. Layer two based scalability solutions are quite a few. You must have heard of many of these. I'll just mention a few: Arbitrum, Optimism, Polygon, etc., etc.
Side chains.
Different side chains, different
parent-child chains.
Parachain architectures, etc., where you have a relay chain and multiple parachains, or you have side chains, or you have, a multi-chain ecosystem and so on. So there's layer two architectures as well. These can use rollups. These can use a combination of zero knowledge and rollups, like ZK rollups. They can use different type of proof compression techniques, different type of Merkleization and integration techniques. So there's many aggregation techniques in layer two. I think, and I apologize, I know I mentioned only 3 or 4 layer twos. There's about 20 I can think of.
Even more names.
Yeah, even
there's
more.
There are different names for the same method, and then
I know. Yeah, so there's quite a few. It can get a little bit confusing too, because one will say they're a layer two that actually is not a layer two. Some will say they're a So the point is, there's different perspectives on that too. There's some layer ones that are layer twos initially and then become layer ones. So there's also that. Anyway, but there's a whole wide world of scalability there. Now, I'm going to talk quickly about my research. I realize I have 11 minutes. I'll keep this very quick. We came up with something called BlockReduce. What it does is it does a nested structure for scalability. So what it does is it takes blocks and breaks them into what are called zones, regions, and prime. This is a 3-level nesting. So are you familiar with Matryoshka dolls, folks? You know what Matryoshka dolls, the Russian dolls?
Yeah.
These are
I thought that's like some technical terms,
No.
That I don't know. Okay.
Those
that
Russian
I know.
dolls.
The little dolls.
Yeah. So think of these are nested blockchains inside blockchain. So this is one blockchain inside a blockchain inside a blockchain.
Got it.
So you can have multiple little blockchains forming one big blockchain that then integrate in one blockchain. That's BlockReduce. We developed it over a few years ago. Turns out this also scales very well. This is a different architecture. So moving on, next slide. So it's a hierarchical architecture where you have dynamical width, where the width The network actually grows, expands, and contracts based on number of transactions. Because this is a whole new architecture for building blockchains, which are hierarchical, we're able to scale very well into tens of thousands of transactions. But this is different from a conventional layer one, layer two, where if you think of a layer one, it's a relay chain, parachains, or main chains, multiple side chains, or sharded state, and so on. So this is none of those. This is a different principle. So this is meant to be an example of how you can actually scale in different ways. So you can scale through relay chain parachains. You can scale through sharded state. You can scale through differential mechanisms to be able to build roll-ups and layer twos on layer one, as well as you can scale through this mechanism of doing hierarchical chains. So chain of chain of chains, right?
So it
Yeah,
basically sounds like scaling solutions. A lot of those is about building up and down, left and right, inside and out of the existing chain.
yeah, yeah, yeah. So, yeah, so you can build a main chain and then build chains around it, or you can build essentially you can build side chains. You can have chains that communicate with the main chain through different protocols, then put a proof on the main chain, or you can do hierarchical chains like we have done. Anyway, so this is just a visualization. It's a nested set of chains. Yeah. Anyway, so moving on. And I'll
So
skip the math. I'll skip the math. So let me just move, unless you want me to talk about the math, Nina. Should I?
oh no, 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 no. That's too much for
I
this
wasn't sure.
webinar.
Yeah, I
So
wasn't sure.
yeah,
If, yeah.
let's talk about the more, the future looking
Yes.
solutions
Yes.
here.
Yes. So let me speak about the future, right? There are multiple approaches to scalability, as I was saying, layer one, layer two. I agree with Nina that if you change the proof mechanism from proof of work to others, it opens up new dimensions to look into scalability. But the good news, folks, is that because of the whole community coming together over the past 12 plus years and working on scalability, we have more and more approaches. So I believe that scalability is going to be a solved problem. It's not, it's a matter of time. I think the challenges are that we need to scale, given the number of applications, to very large numbers, even beyond credit card companies, as Nina was saying. And so to do that, there's many issues. There's the network latency, there's the database issue, there's the IO balancing issue, there's the load balancing issue. And then if you write to me, I'll send you the full list of issues that have to be solved at minimum. So there's a lot of issues, but they're all solvable. That's the good news. And so working together, I believe we can, as a community, build chains that achieve these low latency numbers with generations. The work being done by the Ethereum community, by different communities, including BNB, others, Polkadot, many others, is all moving in the right direction. And I believe 5 years from now, we will look back and realize that we have ultimately solved this problem. So, yippee for us. We are making good progress in solving this problem. And I'm inviting all of you to come work on this problem. As I said, we're moving in the right direction. It's not fully solved yet, right? Some people will say I can do 10,000, some will say I can do 20,000. In reality, as we make progress, we are all doing the right thing, but we're slowly getting there. I believe we'll be doing, in the next decade, we'll be doing 50 plus thousand transactions a second, maybe even 100,000, but it's a process. And so I'm inviting everybody who's on this call to join us in researching this. If you're interested, please send me a message. I'm happy to be a resource, to share articles with you, research papers with you on this, and to introduce you to new ideas in scaling.
Mm-hmm. And I think you are actually not on Twitter, right?
I'm not on Twitter. I apologize. I used to
Okay.
be, but then I deleted my Twitter. Folks, I'm on Telegram. I'm on email, of course. I'm on
Right, you can
Discord.
find, yeah, you can just Google Sriram Vishwanath professor. His full name, you'll be able to find his website and then find how to
Yep.
contact him.
You can find
Uh,
me on LinkedIn as well. Yep.
Yes, and LinkedIn. And also, so at this time, if you have any questions to ask, please send the questions in through chat. And we have one question about the Ethereum merge. So basically,
Yes.
what happens to other layer twos, particularly proof of stake layer twos, after the Ethereum merge?
So the summary is it depends, right? Many of these L2s have been designed to work post merge, so they anticipated the merge in their design. Majority of the ones have already anticipated the merge. For some of them, there is a challenge, and I won't mention which ones. Some of the L2s that started off as L2s have a roadmap post merge to become L1s of their own. So, and again, I can't mention which ones. So the
Sorry,
sorry,
Sriram. So if
yeah,
you can't mention the names, I totally understand. But could you maybe just explain a little bit what type of layer twos and why they're going to face challenges?
okay. So the re-architecture and associated underlying messaging is going to impact the associated level of security for L2s that have not planned ahead. What that means is that given the post-merge architecture, some L2s have been designed to have post-merge functionality as before from the get-go, right? So they designed it to be that way. Then the whole merge process will go very smoothly for them, and that is many of the very well-known L2s that you know of. There are a few that haven't been designed that way. They were designed for the conventional layer one. So essentially, putting a proof on main chain was their approach from the get-go. And so, without getting into technical details, the summary is those L2s will either have to change how they operate or will have to become an L1 of their own because they'll have to post merge split off from putting a proof on the Ethereum main chain. And
Are they going
so,
to have enough time to do that? So what happens if they haven't been able to do that, after the merge? Or
yes, yes. And let me explain this. Most of the popular ones, will have no issue, right? Because they planned ahead on all of this. It's just a few of them that there's like exactly one I know of that hasn't planned it, but there may
and,
be others, right?
and you're saying like they're minor projects, probably not
The
with a
minor
lot of
project.
users and not a lot
Yeah,
of, okay. So
yeah.
it's not going to have a huge
It's
impact.
not going to have a huge impact. So the
Okay.
summary is it's not going to have a huge impact. If you're working with the popular ones, they have well anticipated the merge, right? So you're not going to have any impact, or not. You're going to have only minor impacts, if any. But there's so many L2s, so that's why I was giving a more careful answer. But yes, the summary is the impact is going to be minor at best.
And since you do research on, scalability, do you anticipate any challenges or potential things that could go wrong with the merge?
Uh, Good question. I have to answer that thoughtfully. So let me think about that. The folks, here's my opinion on this. There's a reason the merge kept getting pushed back, right? As you know, it's been pushed back repeatedly. Now we're saying, it's imminent. We'll see. But there are technical challenges. There is also just the fact that the the advantage and disadvantage in blockchain domain is that once you put something out there, it's there. It's very hard to change. And it's both an advantage and its immutability is both its benefit and its Achilles heel, its disadvantage. And so this process, even though it's been very well thought out by Vitalik and the whole set of folks, the brilliant folks that go behind Ethereum, it has had its stumbling blocks. I do see some challenges. I don't want to. They're very nuanced and technical in nature, so I don't want to. These are not like, oh my god, everything is going to break down type of challenges. These are very nuanced challenges that can be overcome. So, but like anything, the first time you introduce it, it's going to have its stumbling. You know, there's nothing that goes very smoothly the first time you introduce it. So I expect those nuanced challenges to have an impact, but I'm expecting it to be a matter of a few weeks, maybe a month or two before they are addressed. So if you're asking me, are there any challenges? Yes. Are those challenges minor? I think so. So I think the merge will ultimately happen, and there'll be a few stumbling blocks after which it'll go.
So when you say minor, okay, from the scale of 0 to 10 in terms of chaos and things go wrong, like where would you put this minor stumbling level be?
Oh, this is one man's opinion, all right? And by the way, I pulled.
Oh yeah, by the way, a disclaimer, huge disclaimer. This is
Yeah,
only for informational and
yeah,
educational
yes.
purposes only, and we don't want to, we don't want to say anything about specific projects,
Yes.
specific companies. This is
That,
only
that
for
that's
information.
why I'm being very careful in my answer. So I've had people that I know quite well who think that the merge is going to be around a 5 or 6 in terms of stumbling, which I think is high. I've had people think it's going to be in the 1 or 2, but unfortunately for me, I don't know anybody who said it's a 0. Right? That's the thing, because again, it's what is happening is a huge technical change. So the process itself will have a few stumbling blocks. My personal opinion is in between those. I think 5 or 6 is too high. I think 1 or 2 is too low. So it's somewhere in between. But again, I don't believe there's anything that cannot be overcome. So don't. This is not a time to worry about. It's not a time to panic. But on the flip side, I also don't think it is going to be as smooth as people think it is, primarily because of this is a fundamental change that's happening. So there's going to be some issues, none of which I'll talk
Yeah,
about
yeah,
because A, they're too technical, B, they're controversial, so I don't want to discuss
yeah.
them. But the summary is, I think it's somewhere in that range. But I think people who say 5 or 6 are being a little alarmist. I don't think it is that bad.
It's great to have this, very objective view from you. Like,
Oh, my
it's
pleasure.
yeah, not overly confident, but not overly disaster type of screaming for disaster type of talk. So
Yeah.
that's great. And if anybody else have questions, please send in your questions. Otherwise, I have a question
Please.
for you, Sriram,
Mm-hmm.
particularly about the merge. I
Yeah.
mean, there are a lot of sensitivities on the topic, as you say.
Yeah.
There are a lot of things actually people don't like to hear
Yeah.
being discussed.
Yeah.
So
Yeah.
maybe we can picture out more of a more distant future when you say initially, of course, we expect some potential challenges and issues, but those are going to be solved. And after that phase, after those potential a little bit disruption around the whole network, then what's going to be the ultimate um, good case, best case scenario for the Ethereum ecosystem?
So the best case scenario for the Ethereum ecosystem is that together with all the benefits coming from layer 2s and newer architectures, the system reaches a steady state where you're able to scale across all of these L2s to operating at, you know, tens of thousands, if not higher, transactions at very low fees. That's the best case, as you can imagine. It also is ultimately should lead to new applications onboarding onto Ethereum, new people working with Ethereum family, which is there's many other Ethereum-like systems that all benefit, because if EVM does well, then they all do well. So that entire, there'll be a lifting of all boats effectively in the EVM world. That is the ultimate best case scenario. The average case scenario is it doesn't benefit much, meaning, yes, the proof of stake has changed energy consumption, but beyond that, from a scalability and overall ecosystem perspective, not much of a difference is made. And obviously, the worst case scenario is the merge is pulled off very badly. It causes the ecosystem to lose projects, which would be a
Very bad for a lot of people.
very, very bad. So the summary is, if I could predict the future, I would be in the stock market and very rich. So I don't know what to predict, but what I can definitely tell you is that everybody's hoping for the best case. We want this ecosystem to grow. We want to bring on the next billion users into the blockchain ecosystem, whether it be EVM or WASM or COSM WASM or whichever family, right? But EVM has been one of our canonical things we've done since early 2010s, and so we really want that ecosystem to grow, because if that ecosystem grows very well, it'll help everybody. It'll help the entire blockchain system become more, bring on way more people into the blockchain ecosystem, and so we really, really want this to go well at every level, and whatever we can do to make that possible, we should.
Great.
So, all right.
So let's all hope everything goes well with the merge, and blockchain scaling solution gets mature, and we can build the ecosystem to where we all want it to be. Thank you so much, Sriram, for today joining us and giving us a great, fantastic talk on blockchain scaling solutions. Everybody else, thank you for being here today. Remember to subscribe. We're going to have more awesome webinars coming up in the future. So for now, thank you, everyone, and have a great day. Thank you. Bye, Sriram.
Thank you.
Thank you.
Bye-bye.
Bye.